Okay, so last time we reviewed the derivation of the work energy theorem. So first of all, what does the work energy theorem say? Work equals change in energy. Okay. Which of these symbols references a property of the system alone? Which is not just a property. It's not just an attribute of the system alone. Well, do you talk about the energy of something? Is that a word you use? You have a serving of cereal. Do you know the energy contained or describing that bowl of cereal? Yeah, and what terms do we use in everyday life to describe the energy in a bowl of cereal? Calories, right? Calories is the unit there. So, so energy of something, it's a property of the system. So this is energy is we call it a state variable sometimes, or in engineering speak, you call it a property. Okay, so in general, something which is a characteristic of the system is a property. Okay, that property is a term that will have a technical use this semester. It's not just a everyday kind of language thing. When we say a property, we mean a quantity or an attribute which characterizes the state of the system without reference to its environment. Okay, so something will have. You guys think of any other property something might have? Just a number that characterizes something. Density, yeah, right? Density of something. Basically, whenever if you talk about something having it, or you say blank of something else, that indicates that it's a property. What else? Temperature, weight. What did you say? Length, volume, area, color, taste, awesomeness. You know, those are all properties. Okay, but energy is going to be one that comes up a lot in thermal, or won't speak. Well, we talked about this. You guys have heard these words. Enthalpy will be one. Entropy will be one. Things like that. Okay. Work is not a property of the system. You don't have your bowl of cereal doesn't have an amount of, or doesn't have a work associated with it. Why not? Where does work come from? Yeah, it's the interaction. You get that? It's the both, right? It's the interaction between the environment and the system. So this is not a property. This is somehow the interaction. Here's a way to think of it. We haven't really talked about temperature and heat and stuff, but you got a cup of water, right? It has a temperature. Temperature is a property because we talk about temperature of the water. Okay? Now, when we change the temperature, how do you do that? Is there a unique way to do that? No, you could take it, you could dump the cup in your campfire. You could put it in an oven. You could put it in a refrigerator, right? There are many ways to affect a temperature change the property. And therefore, you know, in that case, it's not work, it's actually heat. But the point is going to be that knowing that you have a cup of water alone, and even knowing that its temperature change, doesn't actually tell you how you accomplish that. You need to know more information. You need to know something about the rest of the world to figure that out. So that's kind of, so it's important to know what things are state variables or properties of the system and what things have to do with the environment. For example, in the textbooks, I have all sorts of properties here. There's all sorts of things listed, tabulated for, propane or whatever. Which of these kinds of things do you have a chance to look up in a book that can be tabulated once and for all? It's a property of the system. The energy, right? So things that sit here, those are the kinds of things you can look up in a book. We will do that a lot later in the semester. Things over here, you have to know something about, what kind of machine you have, what kind of design choices you made, and how it runs, and things like that. So it's important to know what are the things that you just look up and what are the things you have to find through knowledge. Okay. All right, so we talked about this, the work energy theorem. When talking about one-dimensional motion, what was the formula we had for work? Physics 1. What was the formula we had for work? What's that? What is it in high school? Can you remember that? Okay, now, we're not going to do force times distance, because that's what you would have if you had constant forces. Let's kind of mathematize that a little bit and make it fancy. We won't just multiply them, but what comes out dimensional using calculus? Does that look like a ratio or a multiplication? Multiplication. So which of our two calculus operations multiplies things rather than dividing things? It's an integral. Right? Think about the units. When you integrate things, the units multiply. The integrand times the differential and multiply. So this is the integral of the force dx for 1D motion and everything. And in general, there really should be a dot product. So I'll go ahead and put that. It should be f dot dx. I was going to make it really rigorous. And this is the work on the system. Okay, so if you do positive work on the system, the energy of the system goes up. If I do negative work on the system, which is the same as like slowing things, kind of putting on the brakes or something, it lowers the energy of the system. All right, we're doing this. We did this on Monday. Yes? Okay. Let's do an example. What's the force of friction for kinetic friction? Kinetic friction. Remember? You have a surface, you have a block, okay, and it's rough. How do you characterize the roughness? Mu, and this because kinetic friction will have mu sub k. We'll just make up a number here. We'll say it's 0.2. It's a dimensionless number. How do you find the force of friction? All right, but in general, it's the normal force that sits there. And in this case, because it's flat, yeah. All right, so I'm going to say that the force of kinetic friction is mu k. Actually, hold on. It's the magnitude. Mu k times the normal force. It's actually the magnitude of the normal force. Why the magnitude? Which way does this force point? Opposite the motion. Opposite the motion. So the right-hand side is, after we figure out, I give you a mass, this will just be a constant. So the right-hand side will be a constant, but if you change directions, the force itself will flip. Okay, so you got to be a little careful with that. So what we're going to have is we're going to have a block that's sliding, and I'm just going to, let's say it slides for 1 meter, and I'm going to give you a mass. I want you to calculate the work done by the friction force. Say the mass is 2 kilograms, and we're going to say that it slides. So find the work if it slides 1 meter to the right. Find the work if it slides 1 meter to the right. Oh, right. So we want the work done by friction on this block as it slides 1 meter to the right. Okay, so who thinks they got it so far? Who's stuck completely? It's okay. All right, so people are a little stuck. All right, let's kind of dive into it. All right, so the force of friction has a magnitude of mu k times the normal force, which is mu k, and the normal force is, well, because it's not accelerating up or down, and the normal force must balance the weight. So it has to equal mg for this problem. If we were on a ramp, we have to do some trigonometry. mg, awesome. Is that correct? Which way is it moving? Which way is friction acting? Left. There's a minus sign. Think about it. There's friction, it's sliding across the floor or the table. Is it going to speed up or slow down? Slow down. So that's a loss of energy. So I better get a negative work in there. Yeah. Okay, so there's using the convention that to the right is positive, to the left is negative. So be negative. Now we're good to go. Okay. So, and these are all constants, so I can actually just put in some numbers here. This is going to be minus 0.2 times 2 kilograms times G, which is 9.81 meters per second squared. So that's about 20, that's about 4, a little less than 4. Well, it's 3.9, right? Negative 3.9, and that'll come out as a kilogram meter per second squared. Okay, so it's a Newton. Right? So that's the formula for the force we should have. And let's so let's evaluate the work. Is the integral of the force dot dx. That dot product doesn't really matter for us. Force dx. And we're going from, say, 0 to 1 meter. So just plug all this in. This is the integral of negative 3.9 newtons dx from 0 to 1 meter. Because that is a constant, you can pull it out. That's kind of nice. It's only because the force is constant along this path. So I end up with 3.9 negative times delta x, which was 1, correct? Mm-hmm. Yeah, 1 meter. So then that comes out to be negative 3.9 Newton meters. What's that known as? A Newton meter. It's a joule. It's a joule. So the answer is negative 3.9 joules. Okay? Makes sense. If I slide a block across the table, it slows down. So the work on it should be negative because it loses energy. So the work on it would be a negative amount. You're really sucking energy out by friction. Okay. What if it went 1 meter, hit a wall, and rebounded 1 meter? So it goes there and back. So it goes 1 meter there, 1 meter back. Tell me how much work is done on it. It goes there and back. Everything else the same. There and back. 0 work. 0 work. Why do you think that? Because they're in the same place. Turn the same place. Okay, so now let's think about that. So when you're going to the right, it's the same exact numbers, same exact calculation. Which way, when you're sliding to the right, which way is the force going? To the left. But when you hit the wall and you rebound, is the force the same or does something happen? It changes. So, so this is a big thing. So normally, like in calculus, if you integrate forwards and then integrate backwards, take a function, integrate it forwards, integrate it backwards, you get 0. And that would be true here if the force was the same formula on going forward as it was on the way back. But what happens is the formula for the force changes, and the reason it changes is because it's not a conservative force. Friction doesn't have a potential energy associated with it. It's not a conservative force. And that's why you lose when you go one way, and guess what? You'll keep on losing when you come back. Sapon, hey, can you hear me? Maybe. I don't know. I want to. Thank you. Well, I'm recording it, so I'll post it. So friction, you lose both ways. So when you go there and back, the work is actually going to be double this. So, you know, a little less than 8. Negative 8.
So would still be negative,
Give me
even though the acceleration of friction is in the positive direction.
Right.
Does that be a positive acceleration?
All right. So I'll answer it in a couple ways. One is just, you know, friction slowing you down both parts. Okay, so that's the physics kind of way to say it. A vector way to say it is the real formula has a dot product. So it's not the sign on dx and it's not the sign on the force, it's the relative angle between them. And they're always 180 apart. That's that. The other way to say it is, Billy, on the forward part, dx is positive because you're integrating quote unquote the right way, but the force is negative. On the rebound, the force is positive, but you're integrating backwards. So it's the limits of integration are backwards, and that's the minus sign. But it doesn't, there's always a minus sign. Okay? Now, what if we had another constant force? So that the thing that made it, so Mason was thinking right, but he was forgetting this minus sign. So, because friction changes directions and it's non-conservative, can we think of a force that is always constant, no matter what? Gravity. Okay? So in that case, Mason's logic would be perfect, because for gravity, the force doesn't change. Force doesn't change. It's the same whether you're going up or down. And then Mason's logic would be right. If you start here, you go up, and you come back to where you start, then what's the work due to gravity? 0. Because gravity is a conservative force. Okay? So there's going to be a special role for quantities or things for which when you integrate them around a closed loop, you get 0. That's going to be a special set of quantities. Things like that are called exact. Okay? Exact means if you integrate around a loop, you get back to to 0. That property is exact. Other things are called inexact, but there's going to be a special role, and it is this role. Things which are inexact are going to live here. Things which are exact are going to live here. Right? If I add up changes in temperature, I increase it, decrease it, I get back to where I started. If you add up all the gains and add up all the losses, they add up to 0. So if you were to integrate changes in temperature around a loop, you get 0. Properties of a system will integrate to 0 on a loop. That'll be a big deal when we get to entropy. Right now, I'm just kind of laying seeds for things to come. All right, it feels like they understood how this went. Yes? Question? Oh, all right. Let's do, okay.
Actually, Sean,
Yeah.
what is in that equation, what does the dx represent?
It's a baby step in the x direction. So the idea is, roughly work is force times change in x, right? For baby steps. So as long as this is approximately true, as long as this is a little differential, a little tiny, infinitesimally small. And what we will do, since I already answered these words, when I have a quantity which is in general inexact, I don't want to say, so this is a baby step, so this needs to be a baby step. What we will do is, if it is an inexact thing, I will use a delta. If it is an exact thing, I'll use a d. Okay? So if you go there and back and you add up to 0, I use d. So I should use d for changes in x. If I increase x and then I go back again, my change in x is 0. So I'm going to use a dx. For work, in general, like the example we just saw. I lose, and I lose some more. It didn't come back to 0. So I'm going to use a delta for things that don't come back to 0. Okay, we will use this over and over and over. So it's weird, maybe, but you'll get used to it. So Mason, in this case, the idea would be you start here, you finish here, and you go through all these little segments, and you're just going to accumulate all the little changes. So your integral of f dx really just means the sum of the force times, if you want, the little, you're just going to add up all the little works done along the way that you accumulate. Okay. Okay. Very good. Let's do another one. Oh, I can't. Yeah, let's do a spring. Let's imagine that you have a spring, and the block is going to push against the spring. And let's assume that the spring, what's the formula for the force due to a spring? Okay, that's the energy, the potential energy of it would have to have. This is, it's actually minus K times the compression from equilibrium. We'll just assume it starts out at equilibrium, so we're just going to, X measures the relative compression. Okay, so think about that. If I move, let's say this starts out at X equals 0. So if I increase X, the spring would resist that, so the force would be negative, so that's why you put that minus sign there. If you were to pull it, the spring to the left, make X negative, it would try to contract, and so you get a positive force. So you need that minus sign to get the kind of restoring feature of a spring. Okay, and let's see, what is the work on the block as it moves 10 centimeters to the right? Find that. Yes?
Ignoring friction.
Ignoring friction, yeah. This is in space. Did I tell you that? Rocket ship. All that. I need to give you a number here. Let's say that K is 5 newtons per meter.
But let's say the top X equals 1.
X equals 0. You just start at 0. Yeah. The real formula for the spring force is the relative. It's the stretch or the relative squeeze, not X. It's actually the relative to equilibrium. But I'm just saying that we just assume equilibrium is at X equals 0, so it's all simple. Yeah. Just not shooting constants. Are you able to hear me, Sapon? Okay, good. you really can kind of mimic what we did for friction. Just change the force and just work it out. But you'll have to do calculus. It's not hard calculus. You can't just say force times distance. What's the formula for work? Okay, so write that down. Yeah. Okay. What's the formula? What's the force due to the spring? No. That's the force at one moment. General formula. Minus k dx. Yeah. Because x is changing. Yeah. Yeah, so you have to allow that to be a variable. Michael, how are we doing? Good? Yeah. That's so when it's fully compressed, that would be the number, but it changes as it's sliding. The compression is changing all the way from 0 to 2.1. It's variable. So this would be minus kx. This is only the force when it's all the way compressed. But you have to go all the way from 0 to that point. So it's continuously changing. So what you want to do is integrate minus kx. Yeah, it's changing all the time. Well, it's an integral. It's powerful. Right? X to the 1 dx. Like,
So it's the negative k.
no, that's derivatives when you're integrating. So when you take the derivative, you lower it. So when you integrate, you increase it and divide by nu.
Oh. Gross.
So minus kx dx.
Oh, okay, so already put that in.
We just hold the line. Yep. That constants can come out. Yep. How are we doing? Okay. So the force is continually changing. So the force is going to be minus k. So you want to integrate force dx. So that's going to integrate minus k x dx. Start in, yeah, and you should from 0 to 1. There you go. It's real fast. No. It's x. Oh, you know, your 0.1 meters. Yeah.
And then you plug in 0.1.
That's only the displacement at one moment. You have to integrate over all the x's from 0 to 1. It's a variable. Minus 5. So it'd be integral minus 5 x dx.
Dude, it's so long ago.
Okay, so let's set this up. The formula for work from 0 to 0.1 meters. Right? That's what I need to evaluate. From 0 to 0.1 meters as it compresses the spring. Are we expecting this to be a positive work or negative work? Just so I know that I don't screw that up. The block coming in, it's pushing against that spring. Is that spring helping it speed up or slow down? Slow down. So I'm expecting a negative work. So if I do this right, it better come out negative. Okay? So I have the work is the integral from 0 meters to 0.1 meter of the force, the spring force, dx. Now, I put in the formula for the spring force. It's the integral 0.1 meters of minus k x dx. And I can't just say it's 0.1 meters because x takes all values, all the way from nothing to 0.1. You don't just use the peak or the biggest or smallest. You use all of them. You have to integrate it. So it's a calculus problem. K is a constant, so that pulls out. So that's going to be minus k times the integral of x dx from 0 to 0.1 meters. How do you integrate x? So if you were taking a derivative of x with respect to x, what would you do? What would you get then? You would lower it by 1 and multiply by the old. So when you integrate, you go backwards. So you're going to add 1 and divide by new. So we're going to add 1 to the exponent, divide by new. So this will become x squared over 2. Okay, so this is going to be minus k times x squared over 2 evaluated between 0 and 0.1 meters. Okay?
So for the first one, why did we want to do it like?
You could have, but remember it was constant. So it was like x to the 0.
Oh, it's because there was no variable value?
Yeah, so it just becomes,
Okay.
yeah, good question. Yep. Okay, so now I've got to plug all this up in. I don't know the numerical value, so I'm going to say it's minus 5 newtons per meter times x squared, so that's going to be 0.1 meters squared divided by 2. So, oh look what happens to the units. I have newtons per meter times meter squared, so it comes out as a newton meter, which is a joule. That came out right. Okay, so that's good. And this is going to be, so it's 2.5 times 0.1 squared. So I've got to shift the decimal point twice. It's going to be 0.025. 2 zeros? Good. Yeah, I get 1 0. I mean, I'm from Indiana, but we can use our fingers. So I'll do that one. All right. So, so I'm going to get 0.025 joules. Okay. Thank you. I put it in there. It's real small, though. I'll make it bigger for you. No, thank you. Awesome. Now, let's do what we did for the friction one. Okay, it goes in, compresses 0.1 meters, and then rebounds back to where it starts. Evaluate the work for that. So it goes this scenario as it compresses, and then it rebounds, and when the block gets back to where it started, what's the work done? And this part would be the same. You could do it that way. Yeah. Let's think of it physically. So with the friction case, it did not come back to 0 because the formula for friction was different in each case. For the spring force, does the formula change? No, it's the same formula both ways. So this is just like you would have in Calc 1, where you take a function, integrate the same function forwards and then backwards. So one time you integrate the right way, quotes, and one time you integrate the wrong way, quote. So what's going to happen to the work? It's going to be 0. So you can do it. The only thing that's going to happen is the integrand will be exactly the same, but on the rebound, the limits are swapped. So you get a minus sign and it adds up to 0, just the way Mason was thinking the other way.
So is the friction equation change because of the use of K?
It's not the use of K. What it is we don't really have a nice formula for the friction force. What we have is a nice formula for the magnitude of the friction force. The minus sign, the direction, you have to look at context. So it's not conservative. That's the thing. It's the minus sign. So here's the thing. The spring force is minus K times X. That's Hooke's law. And I can write that as minus a derivative acting on K x squared over 2. Right? And remember, the definition of a conservative force is it can be written as minus a derivative on something. Here's the something, and that's the potential energy to a spring. Half kx squared. So that's a conservative force. For friction, you can't do it. And the reason you can't do it is that, I'll draw a graph. Let me graph. Let me draw a graph and we'll see what the problem is. So, actually, it's okay. I think one way to think of it is, so the friction force was negative and then a positive, and it jumps. Okay? There's not going to be any reasonable function, any smooth function, for which its derivative is going to change like that. So it's going to involve absolute values and weird things going on, because it goes, that sharp change in the force, how it went from to the left then the right as you change direction. That's not a smooth thing, and so yeah, you're not going to be able to write a potential for that. That's really what's going on. Okay. And spring forces are conservative forces. Springs, we talk about potential energy of a spring. Any energy you put into a spring will come back to you, so it's conservative. Whereas with friction, you put energy into friction, the table just gets hot. You don't get that energy back in a useful way. Right? So that the energy is just gone. That's kind of the big difference. Okay, let's take a 5-minute mask break, go outside, and then keep going. All right, Sapon, I'm going to pause the recording. We're going to take a 5-minute break, and then we'll be back. Forgot to record it. So this semester we're using work by the system, which is W. Differs by a minus sign from the system work on the system. The last thing from Physics 1 that I wanted to review was the rate of change of energy with respect to time. So what do we call the time rate of change of the work? So if I have an engine and it's producing work, useful work to move the car, what do I call the rate of change, like the energy per second? Power. Okay. Power. Your textbook in this semester, I will write this as W dot. That's how people usually write it, but it's the same thing, right? W dot. And so power associated with the time derivative. So what would the units be for power? What are the units of work? Joules.
Joules per second.
Joules per second. Watt is that?
What is it joules you have per second?
Don't. So it's a little, you have to be a little careful because work has a W, but then the unit for power has a W. You just think about what you're doing. You're watching. Okay, so power is the rate of change of it. We won't do tons with power for a while until we get to, we'll do a lot when we get to control volume systems, because we want to know, think about the BPU plant, the power plant. Do I really care how many joules that thing has produced since the time it was opened? No. What I care about is how much per second it can deliver right now. Okay, so when we get to those kinds of questions, this is what we'll use. Right now, we aren't worried about that. Okay, so closed systems, we don't use that so much. Okay, very good. Are there any questions about this stuff before I move on? I'm going to kind of change gears here. So, if you think of something, let me know. Try to answer. Okay. Okay, so we reviewed kind of point particle physics, at least what we needed of it. We need to change language. We talk about different quantities because we're not going to study point particles. We talked about last class. We need to kind of average maybe a cloud of particles, of atoms. You don't want to have to track all the details of each little atom. You want to come up with language to describe the average coarse-grained properties. So, okay, that's why we have to change the language. So we want to talk about fluid properties. First off, what is a fluid?
State of matter.
Okay. Can you give me some examples of a fluid? Water, okay.
Milk.
Liquid water, I assume that? Just making sure.
Yeah.
Did you mean liquid?
What about steam? Is that a fluid?
Yes.
Yeah. So a fluid flows. Okay. The real way you would say it is if you take a fluid, it's a state of matter where if you put it in a container, it will conform to the container. So it will adjust itself to conform to whatever volume you let it occupy. Yes?
Would plasma be a fluid?
Yes. Because it conforms to.
I just did that.
Yeah. We won't talk about plasma. So plasma would be a charged fluid. This semester, we really, with sort of trivial exceptions, we won't talk about charge, and we won't use chemical potential, for example, this semester. But it's not that much harder. It's really just bells and whistles on top of what we're doing. Okay, so it's just a matter of time. If someone's doing like chemical engineering, you would just have to add that little wrinkle on top of what we're doing. Yes?
So for like blood plasma, does that have a charge?
That's different. That's just a different.
Just call it.
A plasma is like an ionized, where the ionized. Yeah, so like inside stars and things like that. Or you're trying to set up fusion reactors and things like that. Or yeah, what are those plasma balls? I don't know. Is that actually a plasma?
I think it's electricity.
Well, it's not. It's
not electricity.
I mean, electricity just moves charges. So, is it that have you really ionized the atoms and then to do that, and that's what you're seeing. I don't know. Anyway. Okay, so two special fluids. We're going to have gases. Gases. And when we talk about gases, what we mean is a fluid where the particles are essentially point-like and don't interact strongly. And the separation between two particles is much larger than the size of the particles. The separation between particles is much, much larger than the size of each particle. Okay? It can be a little subjective. I mean, what do you consider much, much bigger, much, much less? In the extremes, though, it's clear what you mean. So that's for an ideal gas. These assumptions are like rigidly enforced, and then for real gas, you start to soften them. It's just instead of having no interaction between particles, it's just a weak interaction. You have to characterize with that. Okay. And then we will have liquids. Okay, so basically just like the opposite. So you know the particles are close packed. They essentially touch each other. That's not really true necessarily, but they're close together. They're close. It's close to packed. The idea, and they interact. So the particles interact with each other. Okay. So if I was drawing a picture of this, I would say a gas versus a liquid would look like this. In a gas, the particles are spaced out. In a liquid, kind of right on top of each other. Okay? Sorry. But in both of these, they're fluids. So they conform to the shape of the container. If I put a dent in the bottom of the container, the gas will adjust so that they flow. A solid state would be like this, dense, but it wouldn't conform to the shape. So the solid, take a solid, you can put it on a table, you can put it in a bowl, but it's still the same shape. It doesn't conform to the block. It doesn't flow around. Okay. Properties of this that are important. When you have a liquid, it will flow, but to very, very good approximation. Because they're so tightly packed, it's very hard to squeeze it any further. I'm not saying you can't compress it a little bit, but it's very, very hard. So to first approximation, liquids will be incompressible. they're not really incompressible, but right, you take a cup of water, if I wanted to contract it to cut the volume in half, I can't do it with my hands, right? You can't do it. Whereas if you have a balloon, or maybe you can't cut it in half, but you can affect the volume of in a balloon. You can squeeze it a bit. You can't, if it's filled with water, you can't compress it. It might slosh around, but you're not actually going to be able to shrink the volume with pressure. So to first approximation, these are compressible, these are not. And they're all statements. Kind of cool.
Not like when you have hydraulics.
So the reason hydraulic lifts work is because it's not compressible. Right? You fill this cylinder with water, and even the weight of a car doesn't cause it to sag. Like it doesn't compress. So first approximation, of course there might be some negligible. If you filled a hydraulic press with air, then what would happen when if the car were to fall off, then the piston would shoot through the ceiling. That would be a compressible state. But when it's full of water, if the car falls off, well, it's still going to. Is that okay? That kind of makes intuitive sense. All right. Okay, so because fluids and in general our systems will fill volumes, they're not point particles, we need to understand what is volume. How do you describe volume? So what I'm going to do is a little bit of baby Calc 3, and I'll let them fill in more details. We're just getting the story going here. So you don't really need a lot of the math. You just kind of need to understand it. You don't have to be able to do it. There's more culture. So we will want to describe systems according to their volume and mass. So we need to have language for that. So volume is, what it is, right? It's the way that something extends into X, Y, and Z, the 3 dimensions. So if you have some shape, some 3D shape, a blob, a fluid, how would you calculate or how would you characterize or measure its volume? How would you do that? How would you think of it? Well, what I would suggest is start with Legos, or sugar cubes, right? You know how to find the volume of a Lego, length, width, height. And then just build this shape out of Legos. And that would be a good approximation to the volume of the shape. Okay? And then if you made your Legos, no? And if you made your Legos smaller and smaller, you can get a better and better approximation. You would what?
So it's hard to make them curve.
Well, okay, so if my Legos are finite sized, then there'll always be little errors, you won't quite have the curve right. It'll be an approximate answer. But if you make them smaller and smaller and smaller, they can hug the curve, and then it works.
So we have to take a limit.
In Calc 3 you will, and in Physics 2 you will. And this, I really just want you to know the philosophy of what you're doing. You're not actually going to do it. It'll just be obvious. But yes, in Calc 3, that's what multivariable calculus is. You do triple integrals. That just means you, instead of adding up little segments, you're adding up little cubes. It's really just Calc 1 3 times in a row. It's not hard. Okay. So what I would do, to implement that process, to define a volume, is I would make a little Lego or sugar cube, and I make a whole bunch. I would really just build up the shape out of these guys, right? So I build up the shape out of all these little Legos, and then at the end of the day, so it starts out as an approximation, but as I take a limit and make it really small, you can hug any shape as close as you want, it becomes exact. Okay? And the total volume would be, so the total volume, and I'm going to be consistent. We're going to have different V's. We'll have V for volume, we'll have V for velocity, we'll have V for something called specific volume. It'll come up shortly. When I mean volume, I will be careful and write kind of wings on it, so it's clear that it's a capital V. Capital V will always be volume, but I will try to be really careful. All right, so the volume is just going to be, well, you would just add up all of the little cubes. Legos, I guess, or whatever. Okay, that'd be the idea. You find the volume of each little one, you need to add it up. Now, because it's little, how do we indicate that in math class usually? Something really, really small. D. Well, it won't be dx, but you got the right idea. X is because it was a segment, a line segment. Now we need a little volume. So I'm going to say that each one of these has a little bit of volume of size dV. And each one gives you a little bit of volume. So I'm going to say that the total volume is just the sum of all of the dVs. Okay. Now, if you're wondering what that might be, well, take a little cube and I would say, okay, well, that's dx in the x direction, dy in the y direction, and dz in the z direction. So the volume of that would be what? dx, dy, dz. So dv, we won't need this in this class. I'm really just doing it to set you guys up for your other classes. dv is just that. And if you really were doing this honestly, you would do an integral over x, then you do an integral over y, and then you do an integral over z, one right after another. Called iterated integrals. You will learn all about that in Calc 3. You'll be experts at it. In Physics 2, we will do this. Brian took Physics 2 with me. We did a lot of this stuff. Do you agree? He loved it. All day, no, I'm getting the head nod on that one. All right. So, that's the idea. We don't really need all that much. Okay, and then make this into a limit, and to make this exact, we end up with the volume is the integral of all the little volumes. That's how I write that. Okay. All right. Okay. What about mass? Okay, so that's volume. What about mass? Let's keep the same philosophy. So what would you do there? You need to know how much each Lego, how much mass each Lego has, and then you would just add up all the little masses for each Lego. So if I want to do mass, for mass, I would say, okay, the mass, total mass, M, that would just be the sum of all of the little masses. So I would just add them up. I would just, actually, I think your book uses little. Okay, but the mass would just be the sum or integral of all the little masses. that's not a, we know how to measure, we're better at measuring lengths, what it really boils down to. So what we can do is we can change quantities. So rather than talking about adding up each little mass of each little speck, what we will do is introduce the concept of a mass density and then turn the mass integral into a volume integral. So what I will do is define a mass density. And the symbol we will use for densities is rho. And because it's a mass density, I'll go and put an M there. For this semester, that's pretty much it. Sometimes we might have a number density. But basically, that's what we have. And that's going to be the mass per unit volume of each little Lego. So it's going to be, basically it's going to say, as you build this shape up, Lego by Lego by Lego, as you add one more Lego, what's the increase in mass of the region? So it's the rate of change of the total mass as you build it up with little Legos. So that's going to be dm dv. So as you increase the volume by a little bit, you also increase the mass. The rate at which it increases is density. In chemistry, is that how you defined density? What do you call density there? Mass over volume. So they're a little different. What's the difference? Right. So here's what I would say. The density is actually the same. So in order for the derivatives to be the same as just the ratio, when does that happen? It happens when things are constant, slopes are constant. So the stuff you do in chemistry, the formula you learn in chemistry is what you would do if everything's uniform. But if you had a material that was inhomogeneous, so like you had variations on the inside, this is actually how you define density. And density could change. It could be a function of wherever you are. You could imagine I build this shape, and on the top I use steel, on the bottom I use feathers. I don't know why, but whatever. And then the density would vary as you move around in the shape. Okay. Now, having said this, all the time that everything we do will be, when we have steam, it'll be uniform density. When we have liquid water, we'll assume it's uniform density. We're not going to have variations inside our system like that. But this is the precise way to do it. This is the real way to define density. It's not really mass over volume. That would actually determine the average density. Mass over volume is the average density. The density is this. Okay. What are the units that you have for this? Mass over volume. Unit-wise, you just divide them. So that is what? A metric system. So it'd be kilograms per meter cubed. So the units of this are kilograms per meter cubed. If we were wanting to talk about the number of particles in a region, you could define a number density. So you could say each volume is occupied by a certain number of particles, and you get the total number, you just add them all up. And same way you have a number density, define it the same way. Okay. You do the same thing with moles. And I never remember, there's molarity and molality, and I can never remember. One of them is basically this, but instead of mass, you're using moles. Does anybody know or remember? Molarity? Yeah. It's been too long since I took chemistry. Same thing. So they're really all just densities and concentrations. Okay. So if I use the density, I can now write I can take my integral for mass and I can express it using the density. Well, first thing I have to do is I have to check And got 1 plus from COVID is there aren't mathematicians just walking around to make sure I don't screw this up. So I can cheat and I can say, oh, okay, dm, seeing no mathematicians, I can think of that as like almost play like fractions. I can think of that as dm dv dv. It's not exactly it. Well, it's cheating. That's what it is. But anyways, you just kind of follow the nose, pretending things are fractions, and it works out the way you need to. So I can say that the mass, lowercase m, sorry. You said that the mass was the integral of dm, but then I can turn that into the integral of dm dv dv. And since this first bit I gave a name, I called it the density, I learned that the mass equals the integral of the density over the volume. And I should write mass density. Really? Question? So this is the density, this derivative is density. So that's what I have. And that is the way you're actually supposed to calculate masses using a density. Now, if, in which case for us, in this class, for us, density is constant, like in chemistry. So in chemistry, densities were constant. For us, it'll be the same way. If this is constant, what can I do with the density in this integral? Just pull it out. Yeah, so I can say that the mass is density times the integral dv. But what is the integral dv going to equal? The volume. So I get that mass is density times volume. Does that look familiar from chemistry? Yeah. So what we're doing isn't not going to give a different answer than chemistry when those assumptions are valid assumptions. It's okay. Right? Density is constant. You can write it that way. Yeah. Okay. We will do, so this is density. In chemistry class, you talk about density a lot, or molarity, molality. This semester, though, or in most of our applications, we will not use density so much. We'll use a related quantity. So rather than talking about the mass per volume, we will usually talk about the volume per mass. You said, have to get used to it. So we won't use density, we will use its reciprocal. Okay? So we will use density some, but we will mostly use, not density, we will use its reciprocal. Call that specific volume. Specific volume, and the symbol for that is V, and I'll always do kind of a script lowercase v. I'll do it the same way all semester. Okay. Specific volume, and that is, it's equal to, when everything's uniform, which it will always be for us, it equals volume per kilograms, or volume per mass. So the volume divided by mass and it turns out that that's 1 over the density. Okay. When we get in, it'll be clear why this is better. But when you guys did You've seen that in chemistry class, I think. You've seen specific used before. What did you, specific heat, right? What was that? An energy, the amount of heat to get something to the excited state. To increase the temperature by 1 degree, and it was probably per gram is how they did it, but per mass. Per mass. When things are specific, that's going to mean that we do it per mass. So if you see, so we will talk about a specific amount of heat, or a specific amount of work, or a specific enthalpy, or a specific entropy. What that means is you do it per kilogram. So what will happen is in many of our problems, we do everything per kilogram. And then if you want to talk about a teacup, you multiply by the mass in the teacup. If you want to talk about a huge tank, you multiply by the mass in the huge tank, and the units all scale, and all you have to do is just multiply your overall answer by an overall mass. So that's why, rather than doing density, because then it's upside down, you gotta monkey around with it. You just work things out with specific volume. You take your full answer, to multiply it one time by the overall mass, and it comes out the way you want. Okay. All right, we'll have lots more of that. Some numbers. It's useful to have some numbers. I know what's going on. What is the, so I'm going to give you, we're going to fill out a table just to kind of know what some reasonable values might be. Okay. Take a second, I'm going to want you guys to fill this in. So I'm going to have table, some substances. I know the book has many more. Let's go through a few. This is the stuff. This is the density. This is specific volume. So let's see. Let's do water. Now, let's be careful here. In chemistry, what were the units on density then? Grams per centimeter cubed. Be civilized here. Let's not do that. Kilograms per meter cubed is how we're going to do it. Because if you do a centimeter cube, it's like a sugar cube. So that's not going to be a very convenient scale if you're running a power plant. So we want to use kilograms as our base metric. Okay, so we're doing MKS, not CGS. Okay, so for pure water, here's what I will tell you. Does anyone remember what the density was in grams per centimeter cubed? 1. So it's 1 gram per cc. So you got to fix that to get it into civilized units. So kilograms per meter cubed. And then I want you to work out the specific volume. So this is, I want the answer in kilograms per meter cubed, or for specific volume, I want it in meters cubed per kilogram. So there's that. Seawater. Do we expect seawater to be more dense or less dense than pure water? Why? Okay. Do you float better in salt water, or you float better so that you're more buoyant? So that turns out this means that water is more dense. So salt water or seawater, and I'm going to tell you that is 1.03 grams per centimeter cubed. said cc, maybe not everyone knows that. We'll call it centimeters. Centimeters. Okay. What's another one? Let's do mercury. I'll go ahead and tell you this one. It's 13,600 kilograms per meter cubed. So you're probably not going to be lifting a meter cube. You're really probably not going to be lifting a meter cube of many things. Right? A meter cube's a lot. And let's do air. Air is 1.28 kilograms per meter cubed. So in your refrigerator, which is like, a meter cubed roughly in volume, the air inside it has a mass of, a little more than a kilogram, so a couple pounds, 3 pounds of the total weight is just the air itself. Okay, let's stop there. So what I want you to do is I want you to convert these to kilograms per meter cubed, and then work out the specific volumes. Do unit conversions, set up unit ratios, multiply them, cancel the bad stuff, keep the good stuff. Once you get the density, you just take the reciprocal. But I want the answers in kilograms per meter cubed, and I gave it to you I gave these two in screwed up units, so you got to fix that. We will have many unit conversions. We'll have to go between horsepower to watts, to BTUs, to calories per pound. I don't know, weird stuff. Yes. Start with this one. Okay, let's start with 1 gram per centimeter cubed. Kilograms per meter. This grams over centimeters, which means this one needs to be. There's probably 10. So, you're helping your friend move. You've got a fish tank. It's about a meter cubed. And they forgot to drain it. What do you say? You say, no. That's what you say. Or you get to their house and they want you to help, move the water bed by 3 inches. You say, no. Huh? Yeah. They have a hernia.
A waterbed's still a thing?
I don't think so. But I would imagine that only a thing for the people who couldn't figure out a way to drain it and get it out of their house. There used to be stories about people, they put it up to the top of their house or something like that, and they didn't think about the mass involved in the weight, and they take the garden hose and fill it up through the floor. Because it's an insane amount. It's like more than a car, more than a small car. Okay, so let's go through that. 1 gram per centimeter cubed. So I need to multiply that. Well, to go from grams to kilograms, what do I multiply by? divide by that. So I multiply, so I think of it as 1 over 1,000, and I would have kilograms over grams. And then for the other one, for centimeters, I would have 100 centimeters is 1 meter, and I have to do it 3 times. That's usually what throws people off. So this is 1,000, this is 1,000,000, 1,000,000 divided by 1,000 is 1,000. So this equals 1,000 kilograms per meter cubed. So, you know, if you have 3 by 3 by 3 feet, roughly, it's pretty close to a meter cubed. That weighs 1,000 kilograms, which is how many pounds? 2,200 pounds. So yeah, your friend says, oh, I forgot to drain my water bed or forgot to empty the fish tank. Well, give them a hose and say, we're getting it empty because you don't want to do that. Wait, bring it back. Okay, so this is 1,000. The density of water is 1,000 in our units. And therefore, the density of seawater is 1030 kilograms per meter cubed. Now, let's work out the specific volumes of these things. How do you go from density to specific volume? Just take the reciprocal. Yeah, so does anyone have these numbers? So this is going to be 0.001 meters cubed per kilogram. How about this one? Is the specific volume for this going to be bigger or smaller? Smaller, right? The more dense, the smaller the specific volume because they work oppositely. What is it? 0.00097 meters cubed per kilogram. Okay. Mercury.
1.4 times 10 to the negative.
Okay, 10 to the negative 5. Okay, so 1.4 times 10 to the negative 5th meters cubed per kilogram. And what about air?
0.781.
I think it was supposed to be 7.4.
7.4? 7. Okay. All right, so let's stop there. Next class, we will define pressure. We'll talk about hydrostatic equilibrium. We'll have atmospheres and millimeters of mercury and blah, 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 you know, funky units like that. And we will talk about expressing work in terms of pressure. That'll be an important concept for us. Okay. All right, Sapon, we'll see you later.